Our last speaker is Professor Colin Masters, an authority in this area of Alzheimer's, and I think revolutionized this whole area in 1984 when Beiruther and Masters published a paper where they actually purified and sequenced the amyloid constituents of the plaque in Alzheimer's disease. And that was the tone from where the Alzheimer's disease actually went on. And I think a number of papers from his lab, from Colin Masters' lab, actually have a major impact on the clinical trial design and provide prognostic information for subjects at risk. Among many other contributions in this area, I just thought I'd mention a few things about Colin Masters. He had all his education in Western Australia, in the University of Western Australia. His medical science bachelor's degree, the Bachelor of Science degree is MD, and a number of awards and honors, distinctions to his credit. But I will just mention a few. He's a fellow of the Australian Academy of Sciences, a Lifetime Achievement Award in Alzheimer's research. And this morning he is going to talk to us on the beta amyloid protein, which is a critical target for preclinical, prodromal, and clinical Alzheimer's disease modifying therapy. Professor Masters.
So, VG, thank you so much for inviting me here, and congratulations on your achievement in being focused on A-beta as the champion in India to keep the A-beta story focused, because this is where the solutions will come. So, coming at the end of the meeting today is extremely difficult because all of my slides, many of them have been used by other people already, but I will try and be iconoclastic and try and give you a spin and try and help you focus your attention on why A-beta will eventually prove to be the critical target in this disease. Let's see if I can get this to work. For my disclosures, I have an interest in, well, first of all, I'm only interested in A-beta, so forgive me for not talking about tau. And I have the relevant disclosures are that I have an interest in Prana Biotechnology, and I'll be telling you a little bit about their drug. And I'm also a consultant for Lilly, and I'll be talking about their drugs as well. Now, Alzheimer died 100 years ago, but nobody has mentioned that. December 1915. And his real name is Aloysius. Aloysius is his nickname. So if you look at his birth certificate, he was born Aloysius. Now, Mary has told us that it's important to talk about incidence. I couldn't agree with her more. So I thought it would be very important, and I use this slide in different contexts, to put Alzheimer's disease in the context of the other neurodegenerative diseases. The incidence in a population over the age of 65 is 2%, and it of course changes with age. But if you look at the total population of a country, the incidence of Alzheimer's is 1 in 100, or about 3,300 cases per million population. Our colleagues, Parkinson's disease, Stanley, PD is comparatively rare. 1 in 5,000, 200 cases per million. And all of our friends who work on Lewy body disease, frontotemporal dementias, again, we have to put this into context of just how many cases of Alzheimer's disease there are compared to these other diseases. That's why I focus on Alzheimer's disease. And thankfully, I don't have to tell you about the slide because everyone else has done it. Now, when we take the brain of a person with Alzheimer's disease or an age-matched control, and we actually measure the amount of A-beta in the brain, what we find is that in a control brain, on average, and this is frontal cortex, but it could apply to other areas of the brain, there's a total of 2.7 milligrams of A-beta. In the Alzheimer brain, there's a of 9.6 milligrams of A beta. That's taking all the grey matter into account, all the meninges, everything. And then when we fractionate the brain, called a very simple process, and we look and see where the A beta is distributed, we find that less than 1% is in the TBS soluble pool, 5% is in the peripheral membrane associated pool, about 1/3 of the A beta is sitting in a membrane associated pool, and about 2/3 of the A beta is locked away in what we now know are these amyloid plaques. Now, it's very important to understand that these metabolic pools or biochemical pools are in equilibrium, but these equilibria are very complex, and we still don't fully understand the nature of these little arrows that I've thrown here. These pools here, which represent most of the A beta in the brain, are in a very locked away position. And when we give a PET scan or a ligand to bind, and I'll be showing you a lot of the evidence of this shortly, when we're using the new technologies of PET scanning, the ligands bind not to this pool, I think, although I haven't quite pinned that down yet, but are more likely to bind to this pool. So when I show you these PET scans later on, you've got to remember that what we're reporting on here is probably the membrane embedded pool, which is in closer equilibrium with the plaques. However, if we take a sample of CSF and measure the amount of A beta in the CSF, we are probably reflecting the amount of A beta in these pools. So it's very important to understand this. Remember, as the disease progresses, this pool increases and this pool actually diminishes because we see a decrease in the CSF level as the disease progresses. All right, now, for those of you who read the abstract, you'll know that I said there are two basic forms of Alzheimer's disease. One is the autosomal dominantly inherited form that John Morris and others have referred to, and the ones that you're looking at with transgenic mice. These are the forms which are caused by mutations in APP or presenilin 1 and 2. Less than 5% of all cases fall into this familial autosomal dominant category. The mean age at onset is approximately 45 years of age. However, the bulk of Alzheimer's disease in our communities falls into the sporadic form of the disease. Probably 98% of all cases are sporadic. There, the mean age of onset is 80 years. So we've got a fundamental difference in the way that the familial autosomal dominant form expresses itself from the way that sporadic disease expresses itself. Now, thanks to the terrific work of Randy Bateman and his colleagues in John Morris's laboratories at Wash U in St. Louis, Randy has actually been the first to be able to take a live human being and come to grips with the kinetic equilibrium, at least in the cerebrospinal fluid, of the A beta that's measurable there. And when they do that, they find that in sporadic Alzheimer's disease, the production rate of A beta 42 is the same as in controls. However, the clearance rate of A beta in a sporadic case is approximately 50% slower than in a control case. In contrast, when you look at the CSF pool in autosomal dominantly inherited Alzheimer's disease, the production rate of A beta 42 is increased by approximately 20%. This is the fundamental difference between early onset disease and late onset disease. Now, to cut a very long story short, and I'm not going to go into the details here, this is an actual atomic resolution structure of a tetramer of A beta held in place, confined as a fusion protein. It was published 2 or 3 years ago. This is the P3 fragment, but if you added a bit more out here, you'd probably see a little bit more of what the true A beta form is. We think that this tetrameric form is possibly the toxic species that assembles in the brain. And we think, and this of course is a model, that this dimer assembles itself on the outer face of the plasma membrane and then leads to all the changes that Viji told you about in her preceding talk. We don't exactly know how it does this, but how it does it, I suspect, is very non-specific. It interacts with a whole range of other co-inhabiting molecules here. It just screws up the normal synaptic homeostasis. We don't know. This is the metal binding site, this is the hydrophilic, and this is the hydrophobic faces. So that's all I'm going to say about this, that we think that a higher order species, higher than a dimer, is the toxic species. It may be a trimer, we think it's a tetramer, it may be slightly higher, but a lot of the higher order aggregates, such as the A-star 56 that Karen Chow have seen, we suspect that these are artifacts of STS and so on and so on. Now, that's enough on the molecular pathology. I now want to turn my full attention for the remainder of my talk to real live human beings. About 10 years ago, we recognized that we had a very good understanding of the molecular pathogenesis of Alzheimer's disease, but we knew extremely little about the natural history of this disorder. So at the same time as the Americans were forming what they called ADNI, which was the Alzheimer's Disease Neuroimaging Initiative, we formed our counter-ADNI, so to speak, and we called it ADL, Australian Imaging Biomarker and Lifestyle Study of Aging, with a consortium of organisations across Australia, principally from Perth and Melbourne. It was initiated by a federal research organisation called the CSIRO. So it's a longitudinal cohort of approximately, stands now at around 1,500 people, who we bring back into the clinic every 18 months and we examine them, we top and tail, so to speak. We measure their cognition, we talk about their lifestyle factors, we take their bloods. But what we did, which was a lot smarter than what the Americans did, was that we gave them all a PET scan with amyloid ligand. We did this from the beginning because back in 2006 this technology was just becoming on the horizon. The Americans put all their effort into a structural MRI, which in retrospect was not a wise decision. So we have a large cohort of healthy individuals, mean age of about 72, completely cognitively normal. We took subjects who, in the old terminology, we called mild cognitive impairment, and we took subjects who had clearly what we thought at the time was Alzheimer's disease, and we followed them over this period of time. So we now have nearly 5,500 person contact years of observations on this cohort. And many of them have been serially scanned with the PET. And those of you who are familiar with this field will recognize this picture. And as I said at the beginning, this signal with carbon 11 Pittsburgh compound B and now superseded by the F18 compounds shows in a quantifiable fashion the retention signal in a person with Alzheimer's disease compared to a person who has no Alzheimer's disease. The signal here in the brainstem is non-specific binding. But as I said, the nice thing about this technology, it is reasonably quantifiable. You can put numbers to this. It's called the SUVR. It's the ratio of the global assessment of the amount of retention signal here compared to a reference signal in the cerebellum or in the pons. More recently, we now have ligands which are relatively specific for tau. And it's too early for me to present much data that the Harvard group have got more data than we have at this point, but we'll catch up to them in due course. But the tau promises to unlock the mysteries of Alzheimer's disease by showing clearly the relationship between the rates of A beta accumulation and the rates of tau aggregation. But those changes are yet to be fully explored. Now, what we did was, as I said, measured the rates of change of A beta as determined by this PET signal. And when we did the back calculations and integrations and asked the fundamental question, how long does it take to go from the normal to abnormal cutoff of an SUVR of 1.5 through to the mean level of a person who has got full-blown Alzheimer's disease dementia with SUVR of 2.33, the number is 19.2 years. Now, obviously, one decimal point here is overstating the case. But you can see the 95% confidence intervals, and you can see the rate of accumulation in this window is approximately linear. And then after the onset of Alzheimer's disease, you can see that this curve, the sigmoid curve, is beginning to flatten off. You can also ask the reverse question and say, how long do we calculate to go from complete normality through to the cutoff? And we come up with this figure of 12 years. Now, these data are not as robust as the data that we've collected for the central part here. When we look at the spread of values between healthy controls, people who've got mild cognitive impairment, and people with Alzheimer's disease, you can see clearly that there's an overlap. But that's the beauty of this technology, because we are beginning to understand that Alzheimer's disease is actually a continuous spectrum of evolution. All right, now, taking the data, very similar data that's been generated through the Diane study, again, which John has referred to, in which we measured the rates of change of amyloid and CSF changes in those early set familial autosomal dominant cases. And well, first of all, before I get to that, let me just explain this slide here. So this is when we compare the rates of change of A beta deposition, here the cutoff, and here is the cognitive measure of a CDR of 1, which is generally accepted as the cutoff for dementia. We can see the rates of change of A beta, CSF A beta, and then we can see the changes of hippocampal volume, episodic memory change, gray matter volume, and non-memory changes. All of these latter are occurring in the last 5 years of the evolution of this illness before the actual onset of dementia. Now, as I was saying, when we compare those rates of change to the autosomal dominantly inherited cases, what we find is almost complete overlap. In other words, even though the familial cases, 20% overproduction, mean age of onset 45, the rates of change in this group parallel almost exactly the rates of change that we see in the sporadic cases. So here, for example, is the rate of change of A beta deposition, here's the rate of change of cognitive impairment, and here's the rates of change of hippocampal atrophy. So what it's telling us is, even though we have different mechanisms underlying the causation of these two forms of Alzheimer's, the kinetics with which the changes are occurring are very similar, and that is good news, because whatever we discover in terms of therapeutic intervention in familial disease or sporadic disease may be transferable in either direction. Now, as you know, there is a good correlation between a $2,000 PET scan and a $100 CSF test of measuring A beta. And this is shown here in this slide, where you have the SUVRs expressed as a continuous variable here, both from the ADA study and the ADA study. You can see that the relationship between the fall in CSF A beta and the increase in SUVR shows this sort of relationship, where it starts high and then falls down low. This CSF test now is about to be fully automated. You can put it on your lab bench, and when the patient walks in, you can do an LP, and before the patient walks out, you can give them the result of a CSF A beta. All right, now one of the other nice things about ABLE is that we have the power to calculate cognitive change. ADNI didn't have enough people enrolled in the preclinical phases to be able to have the power to get the results that I'm about to tell you about. Other longitudinal studies don't have the power that we have here. These are data that are published, and you can go and see them for yourself elsewhere. So this is looking at ABLE data in preclinical subjects, people who are cognitively normal, over baseline 18, 36, and 54 months, and we now have 72-month data, but it shows essentially the same thing. If we look at these cognitive measures, and it doesn't matter which particular cognitive measure you use, people who have no amyloid in their brain, that is, they're negative by PET scan, show no cognitive changes over this interval of time. And it's from these sorts of studies that I'm prepared to get up now and say to you, if you have no amyloid in the brain, and if you don't have any of these rare forms of frontotemporal dementias and so on and so forth, you would live a long time without getting Alzheimer's disease. Highly unlikely you will get Alzheimer's. If you haven't expressed it by 70 to 80 years of age, you are not going to get Alzheimer's disease when you're 90. That's what the data is beginning to show. However, if you're amyloid positive and you are carrying the E4 allele of ApoE, you're showing this type of a decline. This bar here is the 1.5 standard deviation of departure from normality. People who are operating in this space are cognitively normal and are completely unaware that they have any form of cognitive impairment. If you're E4 negative, that is, if you're a 2 or 3, but no E4, this is your rate of decline. These people hit this curve probably around 6 years, hit this bar. These people may go for 30 years. In other words, depending on your E4 status, the rates of decline in the preclinical stages is very dependent upon your E4 status. Now, when we further stratify this group by your BDNF status, remember there's a similar MET viral polymorphism in the BDNF gene that controls the levels of the mature forms of BDNF in your brain. So that if you're BDNF MET, you have less free BDNF in your brain than if you're BDNF val. So if we stratify these two groups based on that BDNF allelic status, what we find is that if you are BDNF val, it doesn't matter whether you're E4, and if you're E4 negative, you've got this form of trajectory. However, if you're E4 positive and you're carrying the BDNF MET allele, you're going to deteriorate to a point where you're beginning to show overt clinical cognitive impairment within 3 years. In other words, what we are suggesting here is that there is a very strong additive effect of two principal genetic loci, the ApoE and the BDNF. Now, this data obviously needs to be replicated. And we're beginning to get replicative data from the Dian study, but it needs to be repeated independently in other groups by other people. So we await that replication. All right, now I want to spend the last part of my talk just talking about therapeutic intervention targeting A-beta. So we've all seen this pathway. Here's full-length A-beta sitting in the transmembrane orientation. The prime target, of course, is a base. We've run into terrible side effects by targeting gamma secretase because of its essential nature in processing many other proteins. I'm not going to talk about trials relating to inhibition of base because the data there is not yet in the public domain, but will be within the next 24 months. What I'd like to do is tell you about where we're at the moment, that means the field as a whole, is in targeting A-beta itself using antibodies specific for A-beta, monoclonal antibodies, humanized, injected, with the idea that somehow a portion of it will get across the blood-brain barrier and neutralize or help mobilize the toxic species in the brain. I also talk a little bit about compounds which are actually directed at the physicochemical properties of A-beta, things like the flavonoids and antioxidants and things that you're beginning to deal with, but the compound that I'm going to be talking about is a 6-hydroxyquinoline. So let's talk first of all about where the monoclonal antibody strategy fields are, because this has undergone a revolution just in the last few months. There are two principal forms. If you target the C-terminus of A-beta, you're wasting your time, because the C-terminus of A-beta is locked away, it is invisible, locked away in the plaque. So no antibody will actually get to see the C-terminus of A-beta. However, two major strategies are to go after the N-terminal epitope and the mid-region epitope. And the N-terminal epitope was originally targeted by bapineuzumab, more recently by aducanumab, and the Roche antibody called gantenerumab. The mid-region antibody, a term in the region of 16 to 23 of A-beta, is the prime target of solanezumab and crenezumab from Roche. The BAPI epitope, bapineuzumab and aducanumab, differs slightly, is a relatively small epitope of the N-terminus, but it's in an alpha helical conformation. And it's this alpha helical conformation of A-beta which is sitting on the surface of the plaques. So you would expect a priori the antibodies to the N-terminus to go after the plaques, and indeed they do. Aducanumab, which I'll talk about, I'll show you the results in a minute, is a very special antibody developed by Biogen that was discovered by Roger Nish from a human subject. It's an autoantibody against A-beta. Now this autoantibody is seeing the N-terminus, but it's seeing a particular conformation of the N-terminus, which is slightly different from bapineuzumab. So I'm going to show you the results of aducanumab in a moment. The solanezumab and crene see a different type of epitope as the mid-region, and for those of you who follow this field, you'll know that the mid-region is the form which is more exposed in the soluble forms, the oligomeric forms of A-beta. In other words, as A-beta folds and assembles and goes towards, as it's coming out of the membrane, remember it's in an alpha helix and the N-terminus, and the beta sheet form which is sitting in the membrane comes out, the molecule flips around and it bends in a region which is then part of this oligomerization process. And this is in the region of 16 to 23. So it's a large epitope which SOLO targets. So we would expect SOLO not to go after the plaques, but to go after the more earlier forms of the oligomeric species. All right. Now I've taken the liberty of taking Biogen's data off the internet and bringing it to you. This is not published work. It's been presented at meetings this year at ADPD and AAIC. This is a phase 1b study, relatively small numbers of subjects, but when we go with increasing doses of aducanumab by intravenous infusion over 1 year, so placebo, 3, 1, 3, 6, 10 in these colors. What they found was that there was a dose-related reduction in the PET signal. So this is the first time that we've begun to see a correlation between giving a drug, targeting A-beta, and a reduction in the PET signal. At the highest doses, at the 10 and 6 milligram, particularly in people who are carrying the E4 allele, there was an immediate reaction, called ARIA, amyloid-related imaging abnormality, in which it looked like a mini cytokine storm was set up, And the antibody is binding to the plaques, it stimulates the microglial reactivity, and you get a certain amount of edema present in the localized areas. What was found was that this side effect could be managed by taking them off the drug, putting them back at a lower dose. More interestingly, however, was the correlation with the reduction in A-beta, that there was an improvement in the mini-mental. It's not quite as neat. I want to get off the N-terminus and go to the mid-region domain. This is data that's now in the public domain from Lilly with their antibody to solanezumab, which is, as I said, region domain epitope. Just to give you the background to this, when you're designing these studies, you go through a placebo-controlled phase where people on drug, I can't actually see this here. This is the treatment arm. This is the placebo arm. So people on the placebo arm have this sort of a trajectory, and people on the active arm have this sort of trajectory. And then at a certain point, if you open the study, make it into an open label study, and you put everyone who was on placebo active, and if the curves stay separate, you can take this as some evidence that you are actually modifying the disease process. If these curves were to meet at some point, it would be an indication that the treatment is more of a symptomatic treatment rather than a disease-modifying treatment. So these are the raw data from the Lilly study. I just point here, this is ADAS-Cog, this is functional activity, this is the CDR sum of boxes, and this is the mini-mental state. So in all of these graphs, it's the same principle. The blue is placebo, the red is active. They're all getting worse. That's the first thing to say. It doesn't matter what the drug did, all these people are getting worse. The people on the placebo were getting worse at approximately 30% more the rate than the people on the drug. And when they went to the open label, the separation of these trajectories was maintained for at least another year and a half after that. Similarly with functional, the CDR sum of boxes and mini-mental. So this antibody is the first to show evidence of disease modification and a slowing of by a factor of 30% in mild cases of Alzheimer's disease. This effect was seen in the moderate case of Alzheimer's disease. By the time you get in the moderate phase, it's too late. So there's great optimism now that if we get this drug into before the disease actually starts, we might have a better. I also mentioned the BACE inhibitors. I want to tell you a little bit about the Pranabiotechnology drug, which is 8-hydroxyquinone, which we believe targets and stabilizes the dimer of A-beta. So the idea, beginning back in 1998, was this molecule would compete for a metal on the N-terminus of A-beta, remove the compete with the metal, and allow some interaction to occur with the dimer of A-beta. This was raving back then. We didn't really understand it. The original drug was a great antibiotic, Arquinol, and this was then modified to improve its ability into the brain. Effective in lowering A-beta in the interstitial fluid of transgenic animals, and more recent data, which was published earlier this year, shows that if you just take the synthetic prep of A-beta and sediment it on an analytical ultracentrifuge, you can see these high-order aggregates, and the matter in the presence of the drug PBT2 or Clarquinol stabilizes a dimeric form. And we believe that this dimeric form is non-toxic and is then able to be cleared from the brain. So back in 2008, we published the results of a 3-month study with this drug in 80 subjects. we showed a clear dependent placebo, low dose, high dose effect on CSF-A-beta, lowering CSF-A-beta. We showed a dose effect on benefit in function over a 3-month period. And more recently, we finished another phase 2 study in which we've taken a small number of individuals with amyloid in their brains. These are mild, moderate cases of Alzheimer's disease. They have a value of SUVR of 2.5. The placebos are shown in blue and the drug is shown in red. The placebos were supposed to follow the trajectory of the ABLE cohort, given the starting point value. However, they declined over this time. There was only 15 in this group, so this was seriously underpowered. There was a significant reduction, however, in the actively treated group. So again, there's evidence that this drug has the potential to lower A-beta in the brain, but in this small group, we do not see any benefit in cognition. Now, the field is rapidly now into prevention studies and even pre-prevention studies. In other words, prevention and primary prevention. The one that I know, the A4 study, which has been coordinated by Lisa Spencer in Boston. We are the world's largest site in Melbourne. We're going to recruit approximately 150 individuals who are mean age of about 75, no cognitive impairment, but have got an amyloid signal by PET in their brain. And we'll give them solenoid for 3 years. And we're going to watch the trajectory of decline in this group. We're doing this thing in collaboration with John Morris and Randy Bateman in the pre-symptomatic phases of autosomal dominantly inherited disease. The next phase of this strategy will be deployed even earlier, just looking at the very earliest changes at 1 month. We want to now ask the question, how early can we go people as they are at risk? Is there any amyloid in the brain, and what can we do to these individuals to interfere with the accumulation of A-beta in their brain? All right, so the conclusions of my talk today are that some A-beta directed therapies are beginning to shift the system, but so far the effect is weak, and we're getting better. The trial failed. Every trial that's come up with a negative result has something fundamental about how to move forward. I've told you about the N-terminus versus the mid-region, and I've told you a little bit about targeting the oligomers of A-beta. I'm suggesting that in the future we will have to stratify by genetic risks, such as APOE and possibly BF. We definitely need to understand these chemical pools of A-beta in the brain, and I've spoken to some of your posters about how to try and get at that with these transgenic. And finally, I just want to say that getting a few milligrams of protein out of the brain is not a big, it's simplistically easy to do. It's only a matter of figuring out how to do it. So the way that we're going to do it is that we're going to put whatever works to its maximum tolerated dose. We are going to come at this, as in the oncology field, this with every possible combination and permutation that we can think of. And we're going to develop new clinical designs, which we call a super adaptive. In other words, a cohort of individuals, you set them on the drug, and you look at the effect in real time, every few months. If you've got a biomarker, you don't tell the people who are doing this what the result of the biomarker is, but you've got to shift those biomarkers. Shifting, you keep pushing the dose. If they don't shift, they have no effect. You stop the trial and go on for something else. I'll end on this light note that the Pope is now solidly behind us. He's at last understood what Alzheimer's disease is. He's accused here of of having spiritual Alzheimer's disease and manage them very severely. You must stop as if you've got Alzheimer's disease. And I think it's because he understands this slide, which was passed out yesterday, but yes. So there are the 7 deadly and there are 7 heavenly virtues. These risk, which are the 7 generally accepted possible modifying risk factors for dementia, are not modifiable risk as far as Alzheimer's disease. All factors which play into the cardiovascular atherosclerosis pathways that into your brain as you we must understand these because after the age of 80, we see an increasing proportion of brains that are complicated. These comorbidities in this aging population becomes impossible in the 85-year plus to often at a clinical level distinguish what's and what's underlying neurodegeneration. That for us is a challenge for the future. We must come to grips. These are the people who are the able to a lot of money, and these are the people who are working with them, and these are the people who collaborate with us in the world. Thank you for your attention. On the CTAD that I've just come from, they've announced the plan of their study. We're going to run with the an increasing from 3, 6. We're not going to go to 10, but they're going to start people by their E4 status. So if you're E4 plus, we're going to start you at a lower dose, and then after 6 months, if everything's going all right, we're going to put you onto a higher dose. So they're not, if I remember correctly, they're not going with the highest dose, which is 10 milligrams.
Okay.
But, you know, if everything goes well at the 6 milligram dose, they may well go higher, because this seems to be the problem. Everyone was put off going to a very high dose. So they're worried about this ARIA change.
Yeah. Another question is when you showed that graph of PET scan changes, you mentioned about A beta positive and A beta negative. Have there been any ApoE4 positive negative? Have there been any ApoE4 positives that have no or normal and the PIB PET scans?
Sure. There's lots of people who are carrying the E4 allele who've got no amyloid in their brain.
And will they ever get amyloid?
It depends on their age. So if you're E4 negative and you make it through to 95, I don't think you're going to get it. But we don't know yet because we just haven't done those. Nobody's actually done that work. But E4 is the major risk factor for age at onset.
So another way of putting my question, what percentage of people who have ApoE4 positive results get amyloid in their brain and will get possibly Alzheimer's? What percent?
Well, it depends. But you have to ask that question within a defined age span.
So the likelihood increases with age?
Very much.
Okay.
Yeah, but we don't know what happens after the age of 90, 95 because those studies haven't been done.
So up to the age of 95, what's the percent that are spared?
Well, we heard 50%. If you just take a random sample of Alzheimer's disease, 50% of them have got E4 error. So that means that if you go back in time, that 50%, people with the E4 error.
The same question. The question was, well, you may not have the answer.
I may not have the answer.
If you take a population that got ApoE4,
right.
What's the chance by the age of 95 they're going to have?
Pretty high.
Yeah, pretty high.
Pretty
That's
high.
what I'm saying. It's not 100% though.
It's not 100%.
Okay.
I was curious, how often the administration of antibody is done? Is it intravenous injection?
Yeah, most of them are intravenous, but the Roche antibody can also be given by subcutaneous route. So there's sufficient absorption. But all antibodies suffer from the problem of relative lack of penetration of blood-brain barrier. So Genentech and other companies are trying to make antibodies that will bind to transferrin receptor and get taken up actively across the blood-brain barrier. Your single-chain antibodies may be a much better way of doing this. I'm not an expert on it.
The frequency of the infusion?
Every month. And that costs a lot of money. You're talking about a therapy that could be as much as $80,000 a year. Question is, who's going to pay for it?
Thank you for a convinced talk. You suggested we should be iconoclastic in the beginning of your talk. So, two things you said I want to understand. First, you started saying there's two types of ADs, and then you demonstrate that there's probably more than two types. So I understand you believe there's much more than two types.
I was talking in terms of pathogenesis. So, overproduction versus clearance.
So, do I believe from the trajectory and what you demonstrated that you do believe that there's more than two trajectories and mechanisms of...
So, one of the big things that has just recently come out of the Scarlet Road study, where they had 3,000 people with the prodromal disease, prodromal. Mm-hmm. Some declined, some didn't.
Yep.
And they saw the effect of the drug in the ones who declined, and they saw no effect in the drug with the people who stayed steady. We've got to get on top of that. We have to understand, why do some people deteriorate in the prodromal stages? Now, interestingly, the ApoE effect is nowhere near as strong in the prodromal. Once you've got cognitive impairment, the E4 effect is nowhere near as strong as it is in the preclinical phases.
Now, the second sentence I want to understand is, you say solanezumab ideally should be given, before the disease starts, something like that.
Well, that's the trial, the A4 study.
So, do I understand that you do believe something else is starting the disease?
When does Alzheimer's start? Let's just talk about sporadic disease. We think, doing the back calculations on all the curves that I've shown you, it would be our best guess that it starts around the age of 50 years. What is causing the A-beta to accumulate in the brain is a failure of clearance. What is the failure of clearance? We don't fully understand. It must be related to E4 some way, but there are other mechanisms at play that we don't understand at all.
But isn't that the primary prevention?
Absolutely. It could well be. We have a particular hypothesis, but it's the degradation pathway is related to monocyte macrophage into the brain and taking it out. And if that pathway fails as you get older, that's the primary cause. In terms of ultimate and proximal causes and ultimate causes.
Thank you very much.
Okay.
Brings us to the end of the session, and we'll now adjourn for lunch and reassemble here at 2:10, 2:15 for the workshop on dementia.